Displacement is first thing that we describe, because we know when something is moving, the position of the object will be changing. In linear displacement, we simply get the difference between the linear positions of an object. For example, if let's say this object is here on point A, it moves to a certain direction, then it gets displaced. It ends up here in point B. Then we say that the object has its initial linear position, and then here, this point here is the final linear position. To get the displacement, you simply get the difference between the final, or x, minus x naught. So that would be delta x, simply getting the difference between the final and initial positions of the object. Final being point B, so this would be x. A would correspond to x naught, or the initial position. The same thing can be said for angular displacement, or delta theta. Theta, or the angular position, is simply the position of an object within a circular path, or in this is any point in a circular path, just like when an object is moving from point A to point B. So you are describing the position of the object in that circular path. For example, we have this circular path with some radius. If this object here is spinning in this circular path, let's say it's moving counterclockwise, right? So this point here, where the object is currently, is what we call, let's call it point A. Then after it moves, ends up right here, point B. What we have here are two different positions, just similar to linear, right? Two different positions. One is the ending point and one is the starting point. We call position A, the starting point, as theta naught. The ending point would be theta, or this is the initial angular position, and then we have the final angular position. To determine the angular displacement, you guessed it, it would be delta theta equals theta minus theta naught. Pretty much exactly the same as what we would do with linear displacement. They are what we call analogs. They are analogs of each other. When we say analog, it means that they are the equivalent of each other. Delta theta is the equivalent of delta x if we would try to describe the linear displacement of an object moving in a circle. How is that so? Now, we know, if we look at this particular path here, right, there is a length that has been traveled by the object from point A to point B, right? So it has been moving in that path. Therefore, it would make sense that it covers some distance. That distance from point A to point B, this part here, that's what we call the arc length. Meaning to say, there is a measure of the distance between the 2 points. With that idea, we could say that delta x could be determined as well. You can get the linear displacement of this object moving in a circle if we consider the radius of the path. In a way, we could say that delta theta, or the angular displacement, can be turned into linear displacement. Let's say the radius of the path is 5 meters. So how will we turn delta theta into delta x? Now, arc length in most references is written or is symbolized by the variable s. But it can also be written as delta x. It could also be written as delta x. Since in our class, we have been using delta x to determine the linear displacement, we'll just use delta x as well for arc length because it is actually the same thing. It's just like saying that the distance that the object traveled here is just straightened out into a linear quantity. How do we determine arc length? So arc length, S, is equal to delta theta times R. Or, for the purpose of our discussions, we will be using delta x equals delta theta times R. So it's that simple. So what's going to happen here? If we have this particular path, what would be the arc length or the linear displacement? X would be delta theta times R. So let's say we start here from 0, and then the final would be pi over 2, 1.57 radians. For us to calculate the displacement, for us to determine the linear displacement, we must first calculate the angular displacement given by this equation right here. Delta theta, will be equal to 1.57 radians as our delta theta. Now, to convert this into linear, so we make use of this equation here, substituting 1.57 radians and then multiplying it by the radius of 5 meters. And we come to find that it will be equal to 7. So we find that delta x is equal to 7.85 meters. Are we good with that? So let's have it in reverse. How would we convert a linear displacement into rotational displacement or angular displacement? Simply using delta x equals delta theta times r, we will derive the equation by dividing both sides by r. So we would end up with the equation delta theta equals delta x over r. Now, if we have a given displacement, let's say we are given that the arc length of a path, let's say you are here, the radius is, for example, 10 meters, and then the arc length is 17 meters, for example. 17 meters is the arc length or yung ating delta x. So how will we know the angular displacement if this is the case? Then we simply use the equation that we have here. So it will be given by delta theta is equal to delta x, which is 17 meters, divided by r, which is 10 meters. Meters will cancel, and then it would be radians. Therefore, delta theta is equal to 1.7 radians. Rather simple. If we're okay with this, then we can proceed to the next one, which is linear velocity to angular velocity. We know that the linear velocity, the equation for linear velocity is given by v is equal to delta x over t. From what we have derived, we know that delta x is also equivalent to delta theta times r. So we can plug that into our equation, delta theta r. So our new equation would look something like this. So average velocity would be equal to delta theta r over t. This expression here, delta theta over t, that is omega, or what we call angular velocity. Therefore, we could say that linear velocity is also equal to omega times r. So it's that simple. Where did this omega equals delta theta over t come from? Well, if you haven't noticed yet, delta theta is the analog of delta x. Therefore, if an object is moving in a circular path, obviously time will pass. And if we divide the angular displacement by the time it took the object to move in that path, then we will be able to get a velocity because you're dividing displacement by time. Right? So this time, since we are dealing with angular angular displacement, then what we will get is omega, which will be the angular velocity. The formula actually looks very much like this one. How will we use this particular equation? Now, let's go back here. Okay, for example, the time it took. Time is 2.5 seconds, maybe. 2.5 seconds. From point A to point B, it took 2.5 seconds to 2.5 seconds to complete. Right? So what would be the angular speed? Angular velocity. So you go down here and try to solve it. So we have computed already delta theta, which is about 1.57 radians. 1.57 radians. Time of 2.5 seconds. And we are looking for omega. So using the formula, omega equals delta theta over t. So what do we get? 1.57 radians over 2.5 seconds. Omega would be equal to 0.63 radians per second. So that is our angular velocity. Now, if we want to convert this angular velocity into linear velocity, then we make use of this equation right here. So let's do that. The linear velocity of this object here would be its angular velocity times the radius of the path, which is 0.63 radians per second multiplied by 5 meters, and we get 3.14 meters per second as its linear velocity. So what would happen, let's say, if you're given a velocity, linear velocity, let's say tangential velocity. Object, let's say, is moving in this direction, radius of 4 meters, tangential velocity, v sub t. V sub t is equal to 20 meters per second. 20 meters per second, yeah. Now, what would be its angular velocity? So, we will be using the linear velocity here, the tangential velocity, and convert it into the angular velocity by using our equation earlier. So that would be V is equal to omega r. Then we simply divide both sides by r, and we will be left with the equation omega equals V over r, or simply 20 meters per second over 4 meters. We will cancel meters, and our omega would be equal to 5 radians per second. Finally, we have acceleration. So to cover all the bases, linear acceleration, in our discussions in our class, well, we have already identified, I think we already identified 3 types of accelerations depending on what is happening to the object. So we have centripetal acceleration, or A sub c. We also have linear acceleration, or sometimes yung tangential acceleration. Tangential is also linear. Don't be confused. When we say tangential acceleration, it is a linear acceleration. So that's the tangential acceleration. And alpha being angular acceleration. There are certain ways to determine the acceleration of an object moving in a circular path. Take, for example, centripetal acceleration. So we have tangential velocity squared over r. So let's say we have, let's use this example again. Let's use this example. The tangential velocity of 20 meters per second, what would be the centripetal acceleration? So centripetal acceleration is where? It is here. That is the direction of centripetal acceleration, or A sub c. To determine the centripetal acceleration of this object here, so we simply get the square of the tangential velocity, square the tangential velocity divided by the radius of the path. By the way, r here, radius, by the way, is also called as the radius of curvature. I forgot to mention this. What radius of curvature means is it's how curved is the path that the object travels. So tangential velocity of 20 meters per second squared divided by the radius of 4 meters. That gives us a sub c equal to 400 by 4. That would be 100 meters. 100 meters per second squared. So 100 meters per second squared. How do we convert this uh, from linear going to angular? How do we convert it from linear to angular? We can do it directly from centripetal acceleration. So how do we do it? Here's how. A sub c is equal to tangential velocity squared over r. But we know that this is linear, correct? V sub t, or tangential velocity, is linear. Therefore, we can use the relationship of omega and v, which is v equals omega r. So how would the equation look like? It would look something like this. A sub c equals omega r squared over r. Omega r squared over r. Now, we simplify, and it becomes a sub c is equal to omega squared r squared over r. Then we cancel one of those r's, and we are left with an equation of a sub c is equal to omega squared r. From centripetal acceleration, a sub c, we can get the oh, sorry, this is another way of calculating. Sorry, what I did here is another way of calculating centripetal acceleration. It's not converting acceleration into rotational motion. I'm sorry. Let me correct myself. What I meant was instead of using tangential velocity, you can actually make use of the omega or angular velocity to calculate the centripetal acceleration. That's what I meant. Now, ideally, the answer should also be 100 meters per second squared. And let's try to check that. So a sub c is equal to omega squared. We have calculated that, and that is 5 radians per second. So we use that here. 5 radians per second squared multiplied by r of 4 meters. So what we get is this. 25 radians per second squared times 4. And what do you guess? It's the same. Acceleration, centripetal acceleration is 100 meters per second squared. Exactly the same as this one. The real question here is how you are to get the relationship between the angular and linear kinematics, or linear acceleration, sorry. Now for that part, we may have to look at tangential acceleration or the linear acceleration equation, which is this. This is an expression or a derivation of equation 1 in our kinematic equations. So A is equal to V naught, V minus V naught over T. But we know that V minus V naught is simply delta V. Simply delta V. So we can rewrite this equation into A is equal to delta V over T. Now, we will be using, once again, the relationship of V and omega, which is V is equal to omega R. So we substitute this equation here and plug it into our acceleration equation. We will be left with something looking like this. A is equal to delta omega R over T. Delta omega R over T. So what we see here, delta omega over T is alpha. That's alpha, or also known as angular acceleration. If we have a linear acceleration, A, and we wanted to convert it into, if we have an angular acceleration, we can convert it directly into, let me correct that. A is equal to alpha R. That would be our final form. And this shows the relationship between linear and rotational acceleration. So alpha times R. So if, let's say, we have a linear acceleration, for example, here, 100 meters per second squared. If we have this, we can convert this into angular acceleration. By deriving the formula, we have here, divide both sides by R, and you have guessed it, alpha is equal to A over R. There you go. What would be the equivalent of this 100 meter per second acceleration, linear acceleration, or centripetal acceleration, if we wanted to know the angular acceleration? Then we simply plug in the numbers. Alpha is equal to 100 meters per second squared divided by the radius of 4 meters, and we are left with an answer of alpha equals 25 radians per second squared. That's it. Let's summarize the analogs. Let's get a summary of the analogs. So we have delta x is equal to x minus x naught. This is for linear. Its analog, rotational, is delta theta equals theta minus theta naught. The relationship delta x equals delta theta r. This is the conversion. I mean, this is the relationship. For velocity, we have v is equal to delta x over t. For rotational, we have omega delta theta over t. For the relationship, we have v is equal to omega r. For acceleration, linear is v minus v naught over t. Or we could also write it as a is equal to delta v over t. For rotational, we have alpha equals omega minus omega naught over t, or alpha equals delta omega over t. For the relationship, we have a equals alpha r